And feel free to take off if you want to, and also feel free to turn on your mics or your cameras or something so other people can see you, or at least put a background picture on it, guys, because it is a little weird. That's the hard part about online lecturing is people feel disconnected, and I think the only way sort of to get over that is to actually get up and comb your hair and turn the camera on. So you don't have to leave your mic on all the time, but ask questions like you normally would when stuff that doesn't make sense. Okay, so the definition you guys know of acids and bases is known as the Arrhenius definition, and you may or may not know that you know this, but it goes like this. HCl is an acid, right? And you guys remember like how we know that that is an acid? And or have your chat window open, because that's actually what I'm staring at now. I'm just staring at the chat. Okay. Just sort of located under the camera. You guys remember any of that? Just curious. Redirect my eyes to right under the camera. Right. It's because it has hydrogen in the front, so hopefully you guys remember that. And then the Arrhenius definition, what we say is that when acids are aqueous, that is when they're dissolved in water, they make H plus and Cl minus. And acids produce hydrogen ion when they're placed in water. And so these are really defined by the formula of the compound. And that's how we know acids. And we say that they make H plus. And then bases are things like NaOH, and it's a metal and a hydroxide ion. This is hydroxide, so OH like this. So just a reminder, because you'll see this a lot, this is hydroxide. All right. And so when you put hydroxides in water and they're aqueous, what you get is sodium ion and hydroxide ion like this. And they split up. And the way we tell whether or not it's the way we're going to do that is based on solubility rules. And so when we do acids, the way we know they're going to do this is by formula, that the hydrogen is in the front. That's where it defines acids and bases. So the new definition is the Bronsted-Lowry definition. That's the definition we use mostly in this chapter. And it's defined on how things react. Okay, so it's not just whether or not it has a hydrogen in it. It has to do with how it shows up as a product in a reaction. So we're calling these proton transfer reactions. The reason we call them proton transfer reactions is when you take H plus, right? That's a hydrogen atom, right, without its electrons. So you have H plus. So hydrogen has how many electrons? Where is it on the periodic table? You guys remember? And feel free to say something or type something. Like in a normal class, I can see what you guys are doing. But to give this any value, you really sort of have to participate if you can. You can even use chat. How many protons does hydrogen have? Right? How many does it have? Somebody's got to know this. I'm trying to break the ice here and get somebody to type something. Okay, I'll just tell you guys. It has one proton, right? One proton. And it has one electron. So that's a hydrogen atom. So when you have H plus, this is just a proton. So in an acid-base reaction, the Bronsted-Lowry definition, what we say is it's a proton transfer reaction. So if you have a Bronsted acid, it's the proton donor. And the base will be the proton acceptor. So let's say you have a reaction of HCl and water. So this will be aqueous. But now we can't just say aqueous. We're going to have to show that it's reacting with water, which is a liquid, right? Then the reaction will be HCl is the acid. It's going to donate a proton. So that means it's going to donate an H plus. So like when I do this, it's donating that to that. And so what's that going to do to the formula for H2O? Well, it's going to become H3O plus, and then it loses, right? The HCl is going to lose the hydrogen. So you're just going to have a Cl minus. And just a side note, right? Because this hydrogen went as H plus, the Cl kept the electron, and that's how you get a chloride ion at the end. So this is the acid. So we would call it the Bronsted-Lowry acid. And this is the base, like that. Now, for most of the reactions that we talk about in this chapter, they're equilibrium reactions, and they're going in both directions like this. So remember the equilibrium arrow from chapter 15. You have an arrow going to forward and the reverse direction. And then when you're done with the reaction, then this reaction can also go, I should use my big pointer so you can see it clear. This reaction can also go in the reverse direction, back to the acid and the base. So that means there's an acid and a base on this side of the reaction too. That is, hydronium will donate a proton back. So on the reverse, it's going to go like this. And donate it back. So this is also an acid, hydronium, H3O plus, is known as hydronium. So I'll write that out too, because that's so important. It's one of the oddball polyatomic ions that you learned. You probably promptly forgot, to be honest. That's what I would have done. I don't remember. What was that chapter? Like chapter 3 or 4. That was a long time ago. Okay, so, but hydronium is going to donate back to the chloride, and then it's going to come back to this side of the reaction. So we're going to start on this side, go to the product. So I have an acid and a base going to the right, and then I have an acid and a base going back to the left. But it would be too confusing to say things like HCl is the acid and hydronium is the acid, because that would be like weird, because you'd be using the same description for both. So everything on the product side gets a prefix by the word conjugate. So this is the conjugate acid, and this is the conjugate base. And honestly, if you flip these two around, this reaction around and wrote it backwards, then this would be called the acid, this would be called the base, and then these would be the conjugates. The conjugates are just what are on the product side, but the acid and base is talking about how they behave in the reaction. So, does that make sense? And you can use like the yes, no buttons like this. Right? Just, if you look at the chat window, I don't know what options you have. Yes or no, right? You should have that as well. Ask a question, feel free to say, all right, cool. All right, so that's just to get some stuff out of the way for definitions. And what I'd like to do is skip some of the information in the middle, but give you guys an opportunity to do these ones. And take a moment to think about, which is the acid and which is the base. So let's just look at this reaction here, okay? And then we'll go over like how you're supposed to know. But try to take a guess at what each one of these things are. So for H3PO4, right? What happens there? What do you think of yourself? That to yourself. Well, if you look at the formula, right, you'll notice that it has a 3 here. And this is kind of how we do this. So we don't actually think about it that hard. The 3 here and a 2 here. So it had to be the donor. So this is your acid. And then this went from 2, that didn't show up so well. This goes from 2 to 3. So that has to be the acceptor. So that's the base. So we do our donor and acceptor. And so that's my base. So the base, looking back over here, right? Notice how the acid produces the conjugate base, and the base produces the conjugate acid. So you don't really even have to think too hard about how it's going to happen. If you're looking at the product side over here, first of all, we know it's the conjugate, so we can just write conjugate. And I use just the letter C for conjugate. And then because this was the acid, this is going to be the conjugate base. So dihydrogen phosphate is often referred to as a conjugate base of phosphoric acid. And the conjugate acid, red, oh, sorry. The conjugate acid is hydronium ion. And so it's often said, like you'll get a question that'll say something, what's the conjugate acid of water? And it'll be hydronium ion. So you look to see, right? First thing you're going to look at is what happened to the number of hydrogens. Then you find the acid. As the acid loses H plus, there's a conjugate. Oh, yeah. You can unmute yourself if you want. I prefer people to be unmuted, but that's just what it is. And then, so that's how you do the acid and base. And then the acid loses H plus, and then it makes the conjugate base. And then the base gains an H plus, and it makes the conjugate acid. Okay. So go ahead and try this next one. And by the way, this one, you could have guessed, but it doesn't always work out. You could have guessed that H3PO4 was the acid, so was it going to be the acid? Try doing this one. The NH3, H2O, and then ammonium is ammonium. We haven't seen that guy in a while either. And then hydroxide, of course, we just defined that one again. So which one's the acid in this case? I can leave the notes like this so you can see our little notes. Which one is the acid? Is it NH3 or is it H2O? So I'm just giving you a moment to think about it. So H2O is the acid. Again, because I'm looking here, right, there's a 1 there. We write it as OH minus, but it lost the hydrogen, so that means it's the acid. That means NH3, right? I went from 3 to 4. That's my base. So then I can do this. So this is Ca. This is Cb like this. Oh, that looks like a 0. Let me write a 1 in there like that. All right, so that's how we do it. There'll be questions like this. Identify conjugate acid-base pairs. So this is the word that we'll use. I think I forgot to mention that in actual lecture last night. So conjugate acid-base pairs. Those would be NH3 and NH4 plus. And then it would also be H2O and OH minus. So we refer to those as conjugate acid-base pairs, even though sometimes we list it as base and acid. It doesn't really matter. All right. We skip the neutralization reactions. I'll let you guys sort of go on that. And I'm going to skip the single replacement stuff. That's all in the video. And then I want to talk about this real quick. I forgot to mention this earlier. I want to make a video about this page. Miss Cornell recorded a video, and I haven't had a chance to look at it yet. And I don't know that it's going to do what I want to do. I usually, in class, actually do what's called a titration. Explain it to people. So I want to try to get that done today or tomorrow. Depends on whether or not the college will let me in. I have to get permission to go in. Anyways. So what I want to do next is focus a little bit on the stoichiometry problems that we're going to have from titration data, and I'll explain to you like what kind of numbers you're going to get. I'll just sort of briefly give you an overview of titration, and hopefully it'll help these problems make more sense to you and try to do them in the lectures. But it goes like this. I have a solution and a burette. Now, it has volume markings on the side. So what a burette does is it measures the volume of solution added to a reaction. Okay, so that's kind of what it does. And then underneath that, you're going to have a solution in a flask, right? Or a solid. Sometimes you'll have a solid. Typically, even if you have a solid, you'll add water to it or a solvent to it to make a solution out of it. And you're going to be adding this liquid is going to drip down into here. Okay. So you basically have this. You have a reactant in the burette, and this is usually the other reactant. So this is a reactant to react with what's in the burette. And typically, well, it's not always this way. Typically, this is like sodium hydroxide, let's say, like a base. I should say it's a base, but it doesn't have to be. It can be an acid too. But if that's the base, then this one will be the acid. And then there's an acid-base reaction that takes place. So if it's sodium hydroxide and HCl, let's say this is HCl. Should have written it that way up there. In fact, maybe I'll just do that right next. So this would be NaOH. Now, and here's the thing. You can switch whether or not the acid or base is in one or the other. The idea is you're trying to control their reaction so that you know exactly how much stuff it takes to react with what's in the flask, okay? And the reaction for this one would be an acid-base reaction, and that would be a double replacement, to remember, NaCl. Sorry, this weird spider crawling towards me, I just smashed it. Plus H2O like that. So that's the reaction. And actually there's a substance called an indicator that we put in along with this, and it tells us when the reaction is done. It tells us when we've added exactly enough stuff from the burette to react with exactly the amount of stuff that's in the flask. Okay, so that's the idea of a titration. I'll make the video of that and sort of be recorded. I'm just saying here. We'll see how it goes. It's going to require some editing. So most of the time, these are stoichiometry problems that are titration problems. And there's solution stoichiometry. So it's from that chapter that we do this stuff. Okay? We learn how to do some of this stuff. But I'm going to go over it sort of in detail here. So this is what's going to happen. You start with the data, you read the problem, and you're going to start with any data that allows you to calculate moles. And so if you have mass, you'll use molar mass to get moles. If you have molarity and volume, you'll use that to calculate moles. That's some of the stuff from the last chapter. And then you're usually looking for something. There should probably be a step in here to figure out what you're looking for, but I kind of added that to the last section. So it says, use a chemical reaction to find the moles of what you're looking for. So you have moles of something that you've been given, and then you're going to convert that to something that you're looking for. For example, if you knew the molarity and volume of the sodium hydroxide, you get the moles of sodium hydroxide. In these problems, more times than not, you're going to be looking for moles of HCl. Okay? It's the other reactant. So you'll use a chemical equation to find the moles of what you're looking for, and then you're going to convert the moles to the desired unit, is really what I should say, using any other data that's given. More appropriate. All right. And then I left space because I wanted these two problems on their own. So these are stoichiometry problems. So let's read through this first one, and we'll go ahead and do it. And then we'll read through the second one. There's one other kind of calculation that we have to go over in this section. And then I'll put the worksheet up this morning so that you have a chance to start working on some stuff. Okay, so it says if 32.05 milliliters of 0.15 molar sodium hydroxide is required to titrate a 25 ml sample of HCl to its endpoint. The endpoint is when you stop, when we're up here, and the moles, sorry, and the amount of stuff that you've added is exactly what you need to finish the reaction down here. And they call it the endpoint because that's when you stop, basically. So it says a 32.05 milliliter sample, if 32.05 milliliters of 0.15 molar sodium hydroxide is required to titrate 25.00 milliliter sample of HCl to its endpoint, the molarity of the HCl solution. So we're going to calculate. Bertha, do you have a bad internet connection? Your mic's on. I think it should be. Oh, wait, turn your mic off. Okay. I was going to say, I recorded this lecture already and then and posted it. And the idea is I'm just going over some of the highlights of this lecture for the calculations. And we're going to do a worksheet, and then there's going to be a study session to do the worksheet. At least we came up with one Thursday at 8 o'clock in the evening. If people want to pop in and get some new worksheet stuff done. And I'll be there on Friday from 10 to 2 as well. That's a normal, like I'm on my Friday 10 to 2 if you go. Okay, so what can you use to calculate moles out of this information, right? And what I was talking about before is if you have a volume, right, and you have a molarity, you can calculate moles. So that's actually where you start the problem. And we're looking for, the unit we're looking for is molarity of HCl. So we'll work that in a second. But I can calculate moles. So that's actually what I'm going to do. I'm going to say, well, I want to say the moles of NaOH. That's going to be equal to the volume, 32.05 milliliters. And if you remember what I was telling you to do for the molarity problems, you write this out as this, 0.150 moles per liter, like that. And that's going to tell you how you use that number with the volume. So I can use this number with the milliliters, because the liters will cancel, but I have to get rid of the milli part first, right? So what I'm going to do is do a milliliter to liter conversion. So it's 1,000 milliliters to a liter. And then I'm going to go 0.150 moles of NaOH per liter, and that'll cancel. And now I have my moles of NaOH, and I don't remember the numbers, so I have to type it out. Every time you see me do this in the lecture, I actually pause the recording to do the calculation and check it. Forgot to divide by 1,000. I'm like, that's a giant number. Now it's a really tiny number, so it's 0.004875 moles. And usually these numbers are reasonably small. I mean, they're not big numbers usually. And then it says, what's the chemical reaction? And we'll use this in our conversion. And the chemical reaction is HCl. And then you're going to figure out that that's H2O and NaCl. So this is what you're going to do. You have to find the moles of HCl, because we have the moles of NaOH. We have this already. So we're going to look for the moles of HCl. So you're going to say let's start with this. Moles of HCl is equal to, and then it's 0.004870075, moles of NaOH, and it's 1 mole of NaOH for every, 1 mole of HCl at the top for every 1 mole of NaOH. Now, in this case, the stoichiometry is 1 to 1, so the moles of HCl is the same as the moles of NaOH. That's going to be equal to 0.0048075 moles of HCl. And so then the question is, what are you looking for? And we're looking for molarity, right? What is the molarity of HCl? Molarity of HCl. And by definition, that's the moles of HCl over the volume of HCl in liters, okay? And so you go back through and you say, oh, look, I have 25 mil sample. So this is 25 milliliters. So that's another problem that I'll have to convert. And I have the moles of HCl. So really, I just need to go like this, 0.0048075 moles of HCl HCl, and then I'm dividing it by 25 milliliters, and I'm going to make this go quick. It's actually this, that many liters, so I drop that underneath. And I just did that conversion in my head, so you may have to write it out, but it's the same conversion that we did before. And we just do that math. So I'm going to divide 0.0048, divide that by 0.025, and I get 0.1923, and the units are molarity, they're moles per liter of HCl. So did you follow along with that okay? So what I'll do is do the next problem, and then I'm going to skip to the very end and do a couple of calculations. So here's the next problem. I have a 1 gram sample of magnesium hydroxide. It's titrated with 17.89 milliliters of HCl. So what that means is I have in my burette, I have the hydrochloric acid. So I've switched it right before I had the sodium hydroxide. And then I have a 1 gram sample of magnesium hydroxide. That's in the flask. And I've probably added water to that to make a solution out of it. But it doesn't say any of that, just telling you that's what that means. And we're going to do this problem. And even if you don't understand the problem, right, you can know how to start. So you just look at the information given and decide what can you calculate most. Right? And in this case, you have a volume of HCl, and you have a mass of magnesium hydroxide. And so with a volume, you can't calculate moles without the molarity. In fact, it says calculate the molarity of the HCl. So you're going to start with the mass, because from mass, you can get moles if you have the molar mass. So I'm going to say moles of Mg, I don't know why I'm writing in red line, of MgOH2. And I'm going to start with 1.00 gram sample. And then I'm going to convert that into moles. And so I don't have my phone with me. I just usually use the molar mass app. I need the grams down here, and I need the moles up here, like that. So let me look it up real quick. Yeah, I looked it up last night, but I don't remember what it was. And I'm just going to Google it. So I'm going to say molar mass of magnesium hydroxide. And I don't think I typed that right. Yeah, 58 looks right. Now, sometimes you should click on, when you do stuff like this, you should click on it and make sure it's anhydrous. Because a lot of times it's got water in the formula, but I'm pretty sure that's the correct molar mass. So 58.32 is what I'll use. So we're back to here, 58.32. So now I can do that real quick. And that becomes 0.017. Let's just do a couple more things. 1, 5. We have 3 sig figs in this answer, so let me do one more. 4, 7. We have 3 sig figs because of the 3 here. And this is moles of magnesium hydroxide. Now, so that's, we did part 1, right? Calculated moles. Part 2 is what's the chemical reaction? So you have to write that out. So I'm going to have MgOH2 plus HCl HCl. And again, this is one of those double replacement reactions. So you're going to write out magnesium ion, hydroxide ion, etc. Okay, and then hydrogen ion and chloride ion, and do the double replacement. But for these kinds of acid-base reactions, I'm going to show you a shortcut. And I'm going to write the products out. One of the products is always water. The other one is always the salt from the magnesium and the chloride. But here's the deal. If you have a hydrogen here and you have two OHs here, it's usually 2 to 1. So that's the mole ratio. So that's the chemical reaction. I've got the number for this. So I'm going to need the number for this. So I'm going to say moles of HCl. I'm going to turn a fan on because my hopefully it doesn't. If this makes too much noise, let me know. My computer gets so hot, I actually have a fan off to the side that blows air on it. Otherwise, it overheats and then it slows me down. So I have moles of HCl, and I've calculated the moles of magnesium hydroxide. And so this is MgOH2. And then what I need to do is convert that over using the mole ratio, and I balance my equation. But like I said, if you have two OHs, it's usually 2 in front of the acid. Then it's going to be 2 moles of HCl for every 1 mole of MgOH2. Okay, so I'll do that real quick. I'll just multiply by 2, and the units cancel out, and I end up with 0.03429 moles of HCl. Because the magnesium hydroxide is canceled out with that. And what were we looking for? We're looking for molarity of HCl. So we have molarity of HCl. That's moles of HCl per liter of HCl. Now I already have the moles. That's 0.03429 moles of HCl. And the volume is this. So 17.89 milliliters. If you do the conversion of 1,000 milliliters to 1 liter, then you end up with 0.01789 liters. So I just basically shifted it 3 places. And so then I can take this volume, 0.01789 liters, and get my molarity. Just do the division. So that is 1.92 rounding moles per liter, or 1.92 moles. Like that. Okay. So these problems can be a lot of work, but the nice thing is you always sort of do them the same way. When you do a titration, you figure out what you can calculate moles from, and that's where you start, and then you work towards the answer that you get. If you always have moles of some substance that you can calculate moles of, a chemical reaction between the reactants that are listed, which you have to balance, and then whatever you have to do to get whatever you're looking for down here in the page. You guys okay with that? You followed along okay? Again, I do it when I do this in the video. Every time my lecture is a little bit different. You might pick up other things. Well, that should have posted. Right? Is everybody sort of following along okay? All right, I'm going to go on and I'm going to move on. I'm going to skip all this stuff. And I want to show you a couple of calculations. There's something called the pH scale. And when you calculate the pH, it's the negative log. It's a base 10 log. I'm not going to write the 10 down there every time. But it's a base 10 log of the hydronium ion concentration. So there's also a definition for pOH, and that's the negative log, base 10 again, of the hydroxide ion concentration. Now, when I write hydronium, you can also think of it as H+. So it's kind of the way you learned it, but it's a hydrogen ion concentration. And if you have a strong acid or a strong base, you calculate, for example, I'm going to calculate, these are strong, so strong acid. What are these calculations? So strong acid base pH calculations. The concentration of hydronium or hydroxide for strong acids or bases is just the molarity of the solution. Okay. So if I want to do the pH of a nitric acid solution that's 0.025 molar, I'm going to say pH is negative. So I'm going to take the negative of whatever I get for the log of 0.025, and then we leave the units off and we just close the parentheses like that. So this is one of those calculations that you need to practice because it's not one that you do very often. So I'm going to show you something in just a second on how I did it on this calculator. This is normally what I'll do in class. This comes out to 1.602, like that. So on this calculator, okay, I'm going to have to get rid of the virtual background. Let's put it back. Do from here. Video, end video, stop video, relay. None of those are the options you want. Here, use the virtual background and say none. Yay, messy room in the back. This is my son's room. One of my son's rooms. All right, so you can see this now. See this, yeah, there it is. If you're doing this, you see this button underneath the second function. This is how you use it. Press it once, it says natural log, and you press it again, and it's log. That's how you get it. If I press it again, I don't know what it's going to do. It's going to give me the option to use any base I want. That's awesome. And then it goes back. So it's cycles. So make sure you don't over hit this button because it's going to go away. Right? Now, having said that, there's something called the anti-log. We're going to use this in a second. So I have the virtual background off. I can show you. It's this. This is the anti-log button. It's right underneath. So there's log and there's anti-log. So when you press this, that's the anti-natural log, and this is the anti-base 10 log. Okay. So you press this once and you get that, and you press it again and you get what you're going to be using in this class. So it's this button, right, and this button. And these are known as anti-functions because watch what happens when I put 1 in there. So I just did this. All right, it's the 10 to the log of 1. And when I hit equals, do that again. When I hit equals, it'll be 1. So those two functions, one does something and one undoes it. So that's what we call the anti-log. 10 to the something is the anti. All right, so if I want to calculate POH, we're going to do this problem. I want to calculate POH. It's exactly the same way. The mechanics are the same. They have different meanings, but the math is done the same way. So that'll be 1.602. Okay, so that's sort of stage one of this, okay? So make sure you can do those calculations. Here's stage two. pH plus POH equals 14. Now I'm not going to spend a lot of time explaining that right now. I explain it a little bit up here, okay? And the other relationship you need to know is KW, which is an equilibrium constant, is the concentration of hydronium times the concentration of hydroxide. That's from that equilibrium stuff that we did in chapter 15. Right, and this is chapter 14. This is why I do 15 first, because they bring all these things in that you need from chapter 15 in the last two chapters, and I don't know why they just don't do it first. Yeah, so watch this. I want to calculate for this solution, okay? Turns out any solution that contains, in water, that contains hydroxide also contains hydronium. Okay? You're probably all just looking around in the room to see what you look like. See this lamp right here? This lamp right there? It broke off last night while I was recording. There's actually a little like stem that sticks into the clamp here, and it just kind of fell over. So I guess I just recorded that. So if you want the pH, right, of this solution, then you would say pH is equal to 14 minus POH. So that would be something like 12.4, basically, rounding. We're rounding it for this place here. Okay, so that's the idea of some of these equations. I just want you to be familiar with them. So here's another thing that I wanted to show you. I give you this diagram, and this diagram gives you all the relationships that you need to convert from any 2 points on that circle. So, for example, let's see. I'll put my virtual background back on. We'll be in the San Francisco Bay Area at some point. We'll take a look at this problem. It says calculate the hydronium ion concentration when the solution has a POH of 2.8. Okay? So this is how you use this, and it's a little bit of a crutch. I understand that, but it's a good place to start. And I'll use a highlighter. So where am I starting? Right, I'm starting with POH, and I find it here. And I'm looking for hydronium ion concentration, and that's this down here. So here's the thing. What this is telling me is that I have to do two conversions. And the arrows actually should be like this. They should have double heads on them, because you can go forwards or backwards on these. I just realized that last night, but I didn't do the slide yet, or the figure yet. So here's the deal. Here's POH, here's hydronium. You have to do two calculations to get here. You're going to have to go from here to here, or here to here. You can go either way. And then once you've done that, you can complete the rest of the way to here. And these are the equations you're going to be possibly using at each point. Okay. So I will just tell you that this equation up here is generally less problematic than this equation down. because the top equation involves addition and subtraction, and the bottom equation involves division of numbers with scientific notation. And invariably, that gets screwed up somewhere along the way. So most students, if they have a POH and they need a hydronium, will go the top route instead of the bottom route. Now, if you've got this stuff kind of down, that's great. But it's the same number calculation. So in my sort of professional experience, it's always been better to use the top equation rather than the bottom. The only time that I would use the bottom one is if I was starting from here, one of these two. If I was going from here to here, that's when I would use the bottom one. But again, my experience tells me that most students make fewer problems doing 3 calculations than they do making 1. Okay, so the 3 calculations being from here, they do the pH, then the POH, and they come down here. And it's just that the equations are easier to enter in your calculator. Mathematically, it's much easier to use the bottom stuff. Okay? It's mostly, like I said, a calculator problem. Okay, so we're going to do this one problem, and then I'll call it quits for today because that's very close to the end of the lecture. I guess I've gone a little longer than I thought I was going to go. And then I'll save this mini lecture, and I'll post that along with the lecture. Yeah, so I've got POH, right? And I need to get to hydronium ion concentration. So first step is this one, POH to pH. And the relationship is going to be this one, which then I rearrange. I say POH is equal to 14 minus the pH. So I'm going to say, oh, sorry, I want pH, sorry. So this is POH on this side. So pH is 14 minus POH. So I'm going to say pH equals, and then 14, and it's actually 14.00. I think I didn't write all the sig figs in the diagram. Minus 2.8. That leaves me 12.2. I'll call it 12.0 like that. Then the next thing to do is to go from pH to hydronium, and that's the anti-log. And so what I'm going to do is this. When I'm looking for hydronium, I'll use that equation. So I'll say hydronium concentration that's going to be 10 raised to the negative. Go ahead and I plug in, excuse me, I plug in this number, 12.20. Now, I do the negative in front like this, just to emphasize there's a negative sign there. You could all put this in one parenthesis. Okay? You don't need 2 parentheses. In fact, I would recommend you get rid of these middle 2 and just have it all together. I just do that because it's clear for students to see it. Okay, so when I do that on my calculator, again, I'm going to do my anti-log function. Turn it on first. Anti-log negative 12. And that becomes 6. It's a really tiny number. I talk about why we do this in the lecture. 6.30. That's 31. Sorry. Times 10 to the negative 13. Okay. So that's how you do those problems. Use that diagram, figure out where you're going from where you're starting, and then choose the route that you think you'll make the fewest mistakes on, and practice. I usually give this diagram on the 4th exam. I think it's on the cover sheet, and then not for the final. So your final, you'll have to know these. All right, any questions? Anything you want me to just sort of go over or talk about in general? I'm going to stop the recording.